In the introductory lecture on processes and process management, we discussed briefly a few basic mechanisms related to memory management. The goal of this lesson is to complete our discussion with a more detailed description of OS-level memory management components. Let's remind ourselves, one of the roles of the operating system is to manage the physical resources, in this case the physical memory, DRAM, on behalf of one or more executing processes. In order not to pose any limits on the size and the layout of an address space based on the amount of physical memory or how it's shared with other processes, we said that we will decouple the notion of physical memory from the virtual memory that's used by the address space. In fact, pretty much everything uses virtual addresses, and these are translated to the actual physical addresses where the particular state is stored. The range of the virtual addresses from V0 to Vmax here establishes the amount of virtual memory that's visible in the system, and this can be much larger than the actual amount of physical memory. In order to manage the physical memory, the operating system must then be able to allocate physical memory and also arbitrate how it's being accessed. Allocation requires that the operating system incorporates certain mechanisms or an algorithm as well as data structures so that it can track how physical memory is used and also what is free among the physical memory. In addition, since the physical memory is smaller than this virtual memory, it is likely that some of the contents that are needed in the virtual address space are not present in physical memory. They may be stored on some secondary storage, like on disk. So the operating system must have mechanisms to decide how to basically replace the contents that are currently in physical memory with needed content that's on some temporary storage. So there is basically some dynamic component to the memory management process that determines when content should be brought in from disk and then which contents from memory should be stored on disk, depending on the kinds of processes that are running. The second task, arbitration, requires that the operating system is quickly able to interpret and verify a process memory access. That means that when looking at a virtual address, the OS should quickly be able to translate that virtual address into a physical address and to validate it to verify that that is indeed a legal access. For this, current operating systems rely on a combination of hardware support as well as smartly designed data structures that are used in the process of address translation and validation. The figure here illustrates that the virtual address space is subdivided into fixed-size segments that we call pages. The virtual memory, not to scale these two, is divided into page frames of the same size. In terms of allocation, then, the role of the operating system is to map pages from the virtual memory into page frames of the physical memory. In this type of page-based memory management system, the arbitration of the accesses is done via page tables. Paging is not the only way to decouple the virtual and the physical memories. Another approach is segmentation, so that would be a segment-based memory management approach. With segmentation, the allocation process doesn't use fixed-size pages. Instead, it uses more flexibly sized segments that can then be mapped to some regions in physical memory as well as swapped in and out of physical memory. Arbitration of accesses in order to either translate or validate the appropriate access uses segment registers that are typically supported on modern hardware. Paging is the dominant method used in current operating systems and will primarily focus our discussion on page-based memory management, though we'll mention segments a little bit more later in this lesson again. As I already hinted, memory management isn't purely done by the operating system alone. In order to make these tasks efficient, over the last decades, the hardware has evolved to integrate a number of mechanisms that make it easier, faster, or more reliable to perform allocation and arbitration tasks regarding the memory management. First, every CPU package is equipped with a memory management unit. The CPU issues virtual addresses to the memory management unit, and it's responsible for translating them into the appropriate physical address. Or potentially, the MMU can generate a fault. The faults are an exception or a signal that's generated by the MMU that can indicate one of several things. For instance, it can say that the access is illegal, like for instance that the memory address that's requested hasn't been allocated at all. or it can indicate that there are inadequate permissions to perform a particular access. For instance, the memory reference may be part of a store instruction, so the process is trying to override a particular memory location. However, it doesn't have a write permissions for that particular access. That page is what we call write protected. Or another type of fault may be an indication that the particular page that's being referenced isn't present in memory and must be fetched from disk. Another way hardware supports memory management is by using designated registers during the address translation process. For instance, in a page-based system, there are registers that are used to point to the currently active page table, or in a segment-based memory management, the registers that are used to indicate the base address of the segment, potentially its limit, so its overall size of the segment, maybe the total number of segments, and similar information. Since the memory address translation happens on pretty much every memory reference, most memory management units would integrate a small cache of valid virtual to physical address translations. This is called the translation look-aside buffer, or TLB. The presence of a TLB will make the entire translation process much faster, since if this translation is present in this cache, then there's no need to perform any additional operations to access the page table or the segment and to interpret the validity of the access. And finally, the actual generation of the physical address from the virtual address, so the translation process, that's done by the hardware. The operating system will maintain certain data structures, such as the page tables, to maintain certain information that's necessary for the translation process. However, the actual translation, the hardware performs it. This also implies that the hardware will dictate what type of memory management modes are supported. Can you support paging? Can you support segmentation, or both? So basically, are there any kinds of registers of this sort? It will also potentially imply what kinds of pages can there be, what is the virtual address format as well as the physical address format, since the hardware needs to understand both of these. There are other aspects of memory management that are more flexible in terms of their design, since they're performed in software. For instance, the actual allocation, basically determining which portions of the main memory will be used by which process, that's done by software, or the replacement policies that determine which portions of state will be in main memory versus on disk. So we will focus our discussion on those software aspects of memory management, since that's more relevant from an operating systems course perspective.